Yeah, so I think I can slowly start with the YCN presentation because most of you have already seen. Webinars, we keep this webinar series strong since 2020. We already had crazy amount of these events, so thanks for joining again. For photo contest, these are the winners of this year. You can see these pictures are truly, truly beautiful. And again, it highlights that ceramics, on one hand, we think about macroscopic samples, which are often not very nice, but when we look deeper, it can be just beautiful. Besides this, what happens in online space, we also have in-person events. Last of those events was our fourth YCN workshop, which took place in Tampere in Finland. And this workshop was very special because it wasn't just something like a conference, but it was, we called it writing retreat. And it really was a retreat. We managed to get a very nice hotel at the lakeside. You know, it was very quiet and just beautiful place for writing. And we had writing sessions combined with talks and some guidance. I think it was one of our best best events yet. Here are just a couple of pictures so you can, you know, picture yourself how these events look like if you still haven't taken part yet. And besides writing, of course, there's always networking, which was very, very cool too. Last but not least, currently we are running a special issue in the framework of the ESERS writing retreat that we organized. The special issue is in the Journal of Open Ceramics, which already has an impact factor. It's a Q1 journal. It's an open journal too. And our special issue is called Young Ceramists Leading the Future. And if you, well, what's the benefit by submitting a paper for this issue? Well, first benefit is that there is 50% discount on the article publishing charge, and also you join the competition for 1,000 euros. So I would say it's worth it. Now, student evenings are something we do at every large ESERS conference. So next one will be in next summer in Dresden. So we hope you join. And yeah, just join us and join the community and take part in this amazing work. Now, before I conclude the presentation, I would like to say that we are looking for a new committee member because Nicolas is leaving us, unfortunately. So the call has already ended, but we plan on extending. So if you still think about it, just write to us and we will consider your application. Yeah, so here are just some QR codes to join our social media if you're interested. And thank you for your attention, and let's keep in touch. Now, let me just go back here. So this was just shortly about the Young Ceramist Network, but today is mainly about our speakers and their contributions. So first speaker for today will be Laura Silvestroni, who is a researcher at the Institute of Science, Technology and Sustainability for Ceramics in Faenza, Italy. It's a very beautiful place, speaking from my experience. And Laura's field of expertise is design, processing, and characterization of structural ceramics with emphasis on materials for extreme environments. She is a lead author or co-author of more than 140 manuscripts published in peer-reviewed journals. And on top of that, Laura is the editor of the Journal of the European Ceramic Society and PI or co-PI on grants funded by national or international government agencies and companies. So with this impressive introduction, Laura, floor is yours.
Thank you very much, Sonia, for your kind introduction. It's a great pleasure for me to be a part of these YCN webinars. And I want to start right now with just a few words about what I wanted to be and how I ended. As a little child, I wanted to become a policeman, loving adventure very much, but then I considered it to be too dangerous and opted for a more silent job like a detective. Then growing up, I decided to become a designer, but somehow I ended up at ISSMC University, completely focused on material science and chemistry. And after all, I can say that the main drivers of my characters have been satisfied with my job as a researcher. I studied at the University of Bologna, and I carried out my master thesis and my PhD at ISTEC, now it's called ISSMC, and performed quite a relevant period at the Technical University of Darmstadt in Germany, where I learned to use the TEM, the transmission electron microscopy. And then after having traveled in several international universities and institutes, I became a permanent staff at ISSMC, which is actually 12 kilometers far from home. What I will talk about, since another great webinar on alike materials has been already given some time ago by Professor John Biner, today I will focus about the importance of the microstructure analysis for the understanding of material performance in extreme environments. So extreme environment has a broad meaning that might imply some high speed rate impact, corrosion, high temperature, and ablation, or a combination of thereof. Here the focus is on those structural ceramics that must withstand high thermomechanical loads at temperature above 1500 degrees C. And each of these environments imposes a set of different structural requirements that are achievable only upon a careful tailoring of components, synthesis, route, and processing. And in material science, a detailed study of the microstructural characteristics from the micro down to the nanoscale level is fundamental for the identification of particular features deriving from processing, which are responsible for the specific thermomechanical behavior that we will see in the final component. And only with an overall understanding of the microstructural evolution and behavior under extreme environment, we can take corrective actions and progressively ameliorate the material performance beyond the current state of art. So today, I will present some materials and narrowing down to the severe environment connected to the aerospace, the family of materials known as ultra-high temperature ceramics, UHTC, is the most suitable candidate. Here you can see a list of the most important issues related to the design and manufacture of materials for extreme temperatures. And I will try to touch upon some strategies that we adopted to address each of them. So starting with the densification, you know that borides and carbides have strong covalent bonds, and therefore they require sintering temperature above 2000 degrees C, application of mechanical pressure, and even current. It is difficult to densify such pure borides and carbides without any sintering additive and control the microstructure, so to obtain effective good performance. Furthermore, it is difficult to machine such strong materials. During my master and PhD, I worked on borides and carbide with addition of molybdenum disilicide. At the beginning, I started with the hafnium diboride, then I took by mistake the wrong the wrong tap and opened the family to all zirconium diboride, zirconium carbide, hafnium carbide. So sometimes mistake just broaden your work plan. So why we added molybdenum disilicide? Our goal was to enable the densification without application of pressure, so that we can produce near-net shaped components by pressureless sintering. Molybdenum disilicide has a high melting point, high stiffness, and excellent oxidation resistance. These are examples of the microstructures of zirconium carbides or hafnium carbide with molybdenum disilicide that were sintered in flowing argon at 1950 degrees C. And we performed a very thorough microstructural characterization. These were the very first materials, so I was not very skilled yet with the material preparation. So the area of the thin specimen were quite thin, and I became quite crazy to find, to identify the triple joints in thicker areas and so on. We did the same on the borides, and here for the first time we identified like the core shell structure, where the core is which is a particular morphology of the grains, where the core is the original boride, zirconium diboride, and the shell is a solid solution that grows around the core and contains the gas element that we added with the sintering additive, molybdenum in this case. So to promote the densification, the baseline is to use some fine starting particles, not too fine because otherwise we introduce too much amount of oxygen, but not too coarse so that the matter transfer mechanism are enhanced. Then using the strategy of the transit liquid phase is a good option because at the sintering temperature we have a liquid phase that cleans the surface oxide, which hinder the densification of borides and carbides and acts as a grain lubricant. Having a poor wettability of the transient liquid phase towards the matrix is also desired because it helps, on one hand, it helps the grain rearrangement, but it leaves clean grain boundaries and doesn't negatively impact on the mechanical properties at high temperature. So our selection felt on molybdenum silicide because it has a brittle to ductile transition, which is ductile and fills the voids due to its plasticity, and it also had some solubility within the matrix, so that we could form some core shell structures and hierarchical microstructure that you will see in the next slides. So now I want to tell you the story of this great and lucky material based on zirconium diboride, silicon carbide, and tungsten carbide, which exhibited a core bending strength about 600 megapascal at room temperature. It increased to around 800 megapascal at 1800 degrees C and remained over 600 megapascal up to 2100 degrees C. And these results were never achieved before and were rather impressive and puzzled us to deeper investigate on the reasons that by chance we made this material and we got this such super high strength. As main microstructure features, it was fully dense with clean grain boundaries and mean grain size around 1 micron, nothing special. The grains were featured by the core shell with a pure core zirconium diboride and a solid solution around the core containing tungsten. Most of the tungsten carbide was converted into tungsten diboride phase due to the reducing environment. And in addition, we noticed on the fracture surface that we detected these bright elongated particles and zigzag fracture pattern. To get further deeper into, I did some TM analysis on the broken bars upon high temperature strength, and you can see an intense dislocation activity in the boride grains that formed real tangles of dislocation, and these intersect and interact among each other, forming polygonized dislocation walls, which actually led to a grain refinement from the original micron size down to the nanoscale. Then I checked the second phases, and both silicon carbide and tungsten carbide displayed stacking faults, which are beneficial for crack deflection. And then if you look at silicon carbide particles, these here, you can see that when the crack crosses the line defects, crack deviation occurs, whereas when the cracks meets the defect along its longitudinal direction, it proceeds straight without any deflection. The grain junctions remained cleaned and like in the as-sintered material, except when we had two adjacent silicon carbide grains in this region, where we observed some glass between the two. So the choice of adding just a little bit of silicon carbide was good in avoiding creep at high temperature. I went back to the microscope, this time on an annealed sample of the same composition, but just thermally treated to boost the phenomena that were just highlighted, slightly highlighted in the sinter material, and to better evidence what was the responsible. And on the polished surface, we found that the core shell was preserved, but just the core was reduced and the shell region was enlarged. There was coalescence of silicon carbide grains and again, the bright precipitate. By TEM, we were finally able to label these precipitates as metallic tungsten, from which the dislocation departed. So we had some nano-metallic particles into a micron-sized boride grain. To justify the strengthening at ultra-high temperature, we considered Griffith's equation and the attributes that might have changed during the test, either acting on the toughness or on the flow size, which is actually related to the grain size. We collected a series of positive factors, starting from the refractoriness of the matrix, of course, with the small grain size, which did not increase, but actually refined upon loading by dislocation intersection. The grain boundaries were clean, thanks to the choice of tungsten carbide as additive, which cleaned all oxides. Then we considered another hypothesis related to the formation of a healing outermost glassy layer at high temperature. But actually the tests were done in argon, and so no glass was formed. So this factor was discarded. Then we had hierarchical microstructure with nano-sized tungsten particles acting as reinforcing space. And this tungsten was ductile at the testing temperature and locally toughened the material. We also hypothesized local toughening occurring at ultra-high temperature, including silicon carbide and tungsten diboride, boride platelets pull out. We had tungsten precipitation from the shell in the shell solution. And this rejected tungsten is ductile at extremely tough at high temperature, so it could absorb fracture energy. We also considered the mean grain size that was retained during the test at up to 2100 degrees C, but actually the shell region enlarged. So a larger volume fraction of material was actually reinforced by these precipitates, and the similar toughening at nanoscale in the shell was amplified. Here I collect all data available on up to the ultra high temperature regime, which is commonly defined at 1600 degrees C. And here is a dotted line. You see the boundary of 300 megapascals, which is considered reasonable for structural application in the aerospace sector. So in gray and black data, I reported data from mostly pure zirconium diboride obtained from the Air Force labs in the 70s and more recently from the MS&T group. Both of them were featured by quite large range from 5 to 20 microns, and as such the strength was not exceptional, did not exceed 400 megapascal and decreased to 150 megapascal. We prepared then another material in blue, where the second phase was completely consumed during the thermal treatment, but still had a finer grain size, resulting in a constant strength here in blue around 400 megapascal from room temperature up to 1800 degrees C. Another interesting result was obtained for our hafnium diboride based system that you see in orange and red. The orange is the S-sintered and the red one is the annealed here. We measured strength increase of 300 after the annealing due to the development of the shell with the tungsten inclusion. Then we arrived to the light green materials where the annealing the darker gray, had an opposite effect. It didn't increase because it actually relieved the dislocation structure and increased the size of the tungsten particles, both of which reduced the high temperature strength. The highest strength was found, for this fluo green here, that belonged to a zirconium diboride material, where the addition of tungsten carbide was increased to 15 volume%. And this composition resulted in an unprecedented strength of 1 gigapascal at 1800 centigrade that remained over 850 up to 1900 degrees C. Moving beyond this temperature, the ceramic underwent plastic deformation that we attribute to the ductility of the dispersed tungsten boride phase and the approach of the eutectic temperature. Anyway, we didn't have a brittle failure. Another interesting aspect which we found working on several systems containing zirconium diboride and tungsten, molybdenum, or tantalum, is that depending on the system, on the transition metal, we observe precipitation of non-inclusion of different chemistry, borides, metal, carbide, and shape. And we suppose this factor to be related to the local partial pressure within the furnace. One question that we still have in mind and we haven't answered yet is the possibility to tune the chemistry of the precipitates in the form of metal borides or carbides by manipulating, by using different furnaces, by changing the sintering environment. We still don't know if it's possible or not. We also wondered if having grains, core shell grains made of complete solid solution, like eliminating the core, would be beneficial than the core shell structure. But the answer is no, since the elimination of the core and the formation of a homogeneous shell mean the elimination of one discontinuity, that is the dislocation walls present at the core shell interface. And actually, these linear faults are conductive to a grain refinement and to increase plasticity upon testing at elevated temperature. So, the K factor for super strong ceramics in the ultra high temperature regimes are microstructure heterogeneities spanning from length scale from the micro, second phase, grain cores, to the nano, which include solid solutions in the shell, dislocation, and precipitates. These features interact during the formation, and these might have the potential to achieve superior properties and temper the strength ductility paradox in the ultra high temperature regimes. Let's move now to the oxidation of zirconium diboride, which is again quite complex topic. Zirconium diboride alone doesn't really work because it forms boron oxide, which is volatile at definitely too low temperature for such materials. But at higher temperature, it forms it leaves just a naked porous zirconium oxide skeleton, which is not really sufficient. The addition of silicon carbide prolonged a little bit the lifetime of the zirconium diboride, but still, as we move to above 1700 degrees C, we start having problems of active oxidation in the subsurface, and again, we don't achieve the 2200 that could be possibly achieved in the hypersonic application. Therefore, we decided to add some transition metal to modify the glass viscosity, boiling temperature, and saturation. And the transition metal could modify also the solid skeleton, the zirconium oxide, that is hindering the martensitic transformation, limit the expansion of volume, form a tactic melt that could melt and possibly slow down the oxygen penetration within the core. So here you can see how the addition of a transition metal strongly impacts on the oxidation behavior. Here we have zirconium diboride additivated with zirconium, molybdenum, tantalum, or tungsten silicide, and oxidized at 1200, 1350, 1500, and 1650. You can see here that what works really good at up to 1500 degrees C is not really optimal if you increase the oxidation temperature a little bit. And this is related to the intergranular phases. So I would just concentrate on this most striking example with tantalum. And here in the cross section, we can appreciate very complex microstructural architecture at 1500 and 1650 degrees C. Without entering into details, we have a mixture of molten glass, solid phases, polytypic transformation, dissolution and reprecipitation. Many things are happening here. But if we go farther deeper with and check each layer by TM and with a lot of patience and luck, maybe you can recognize, let me just jump to the point, you can recognize in this structure our core shell structure. So actually zirconium diboride oxidized into zirconia, and our tantalum non-inclusion reacted with the boron oxide released by the matrix and formed tantalum diboride. So far so good. By oxidation we form a boride, good. But the problem is that until we are at low oxygen partial pressure in the subscale, these tantalum diboride particles are protected and very effective. However, as the oxidation becomes more aggressive and reaching in oxygen or increase the temperature, tantalum diboride oxidation occurs and forms tantala, which is beautiful from a microstructural point of view, but it's accompanied by a very large volume expansion that destroys the zirconia skeleton. So in an extreme simplification, this is how the core shell evolves upon oxidation. So zirconium diboride is the compound that most favorably oxidized, and its oxidation protects the particles which remains nestled inside. Then, depending on the system, the particle evolve as boride or remain as metal. And in turn, we might have problems or not if the oxidizing spaces at the testing temperature is solid and might have some volume expansion, or liquid, and in that case could fill the voids, or it's vapor, and in this case would create bubbles and leave the system. One way to foresee what phase I will have in my oxidized shell is to use the phase stability diagrams, which look more or less like these, and they plot the stability areas of condensed phases versus temperature and the chemical potential. You can decide the temperature that you want to test, and you can see that at the same boron oxide and oxygen partial pressure, in one case we have zirconia, whereas in the other case we have tantalum diboride or tantala if we increase the temperature, and this fitted very well with our experimental finding. So to make our UHTC more oxidation resistant, we first need a little bit of silica former phase, so to create an initial glass ceiling, but not too much, otherwise we will have other troubles. We should have a homogeneous distribution of the second phase, so having a complete solid solution is actually beneficial for the oxidation. The capability to condense as boride in subscale is also favorable because you slow down the oxidation, but the nature of the phase that form depends on the gradient partial pressure. We should try to look for high stability field in the region of the highest oxygen partial pressure, and one of the candidates is rhenium, but it's not really economically affordable. Because if we don't have large expansion at the intergranular phases of zirconium oxide, we would limit the tensional stress and the architecture destruction. So we have another problem, fracture toughness. In an attempt to mitigate the poor failure tolerance of UHTCs, the research on a new class of materials that merges UHTC and matrix and CMC, ceramic matrix composites, has been recently launched and is called UHTCMC. Looking at the fiber portfolio, there is a jungle. You can vary the length, continuous or short, milled, less milled, the composition, silicon carbide, carbon, the crystallinity, add a coating, without a coating, and it's really a large playground. And it's possible, it's very possible, that before measuring a considerable fracture toughness increase, you will have to pay attention to several factors. And first of all is the sintering temperature, which is dictated by the sintering additive, and will create some troubles with the fibers, which you find in several generations, more or less crystallized. And every generation, every type of fiber, also carbon fiber, has a different reactivity. So it's not really straightforward. Here you can see some examples of the interaction between silicon carbide fibers of second generation, the high nickel, and the third generation Tyrreno SA3 with the same matrix, and you can see how these fibers progressively deteriorate with increasing sintering temperature. So it is a bargain between the matrix densification and the fiber degeneration. So the path from the raw fiber to the fiber in the sintered composite passes through some fundamental phenomena that derive from the fiber composition. And for example, in the case of silicon carbide, includes silicon oxycarbide softening, which is included in the raw fiber, carbon migration outwards, silicon carbide crystallite coarsening, and then we have, of course, cleaning of the borides particles and formation of silicon carbide platelets well anchored to the matrix. A similar trend is observed, of course, also on the carbon fibers, where the extent of the interaction is defined by their the production process of the raw fibers. That is, it depends if they are if they derives from pan-based or pitch-based. Furthermore, beside this general interaction, we have noticed that beside the additive, the strength of the interface domain between fiber and matrix varies independent of the fiber volume fraction. We have stronger interaction for low fiber content and weaker interaction for high fiber content. In addition, the fiber, either silicon carbide or carbon, oxidize preferentially as compared to the boride refractory matrix. So to help with the simultaneous issues of fiber degeneration by interaction with the additive, efficacy of the fiber on the mechanical properties, and preferential oxidation, we have the smart and the relatively simple approach of the functionally graded concept, where we can design a UHTC-rich outermost layer that protects from ablation, and a progressively fiber-rich core that provides failure tolerance and thermal shock resistance, besides making the composite overall much lighter. But, of course, we have to take care of prevention of fiber deterioration upon excessive interaction with the additive. So we need to actually find the right one, and we can actually change the sintering additive across the thickness of the composite. Then we have to couple layers of different composition and thickness that can induce cracking instead of increasing toughness. And this is also something that must be considered. And of course, we have to create our component, and manufacturing is also an issue. But this can be done by several methods that include dry pressing, of the various powder fiber mixtures, or slip casting, or even 3D printing. So a new star is born, that is the UHTCMC class of material that enables a very broad variability of architectures, fiber alignment into random 2D, 1D, and so on. Functional graded materials are, I think, a valid approach to make a compromise on our material processing. But of course, the blanket is always a bit too short, and there is a series of careful considerations that must be taken into account. One quick note on the complex UHTC shapes. UHTC coating can be realized by atmospheric or shrouded plasma spray, which are a rather economic route and enable to coat also a relatively complex shape. But again, we must optimize the granules feedstock, which must possess the proper composition, size, and compactness to correctly adhere to the substrate and protect from ablation. The last comment on the additive manufacturing, which has become a very popular and convenient approach in the last years. By direct ink writing, it is possible to extrude UHTC-based paste, also containing fiber, and create a plethora of complicated shapes. There are several cool aspects related to this technology, like, for example, we can add up to 60% short fibers for 3D printing. We can align the fiber and increase the failure tolerance and the fracture toughness. We can even hot press such a relatively complex shape by use of a critical powder bed, and you can even merge different shaping route like direct ink writing, deep coating, and other, and create a complex shape with a functionally graded architecture. So the key aspect that it is essential in the development of complex shapes and complex architecture is the coupling of an experimental part with a simulation one, which can predict the stress states at the various interface and estimate the toughening degree. So what you should actually keep in mind after this thrill trip through UHTC issues and patches is that good work is better than a bad work, which is quite obvious. So take your time, think twice, and operate cautiously. However, a bad work is also a good result and can teach a lot. So pay attention also to bad works. Then patience and endurance pay back. So for example, I couldn't have good TM pictures and good stories to tell you if I hadn't spent a lot of time in preparing good samples. Then of course there are other factors that play a role, but I will not enter into detail. Then your materials contain all information that enables you to ameliorate their performance. So spend time in studying the microstructure, talk to them, try to understand what they want to tell you. And at last, catch the train. The more you can, all you can, because they might pass just once and could be pivotal in your career and private life too. Now I would like to acknowledge ISTEC working group, MSMT for the high temperature strength, and the University of Naples for the oxidation, and of course the funding project that contributed to the achievement of these results. And thank you for your kind patience and attention.
Thank you, Laura, for your beautiful presentation. I completely agree with you that hard work pays back. And I would like to ask everybody, if you have any questions for Laura, but also for Dawid, please write them in the chat. And after the second presentation, we will read them and our speakers will respond. So thank you very much once again. And now I would like to invite Dawid to join us. Dawid is our second speaker and is a researcher in the Faculty of Material Science and Ceramics at the AGH University of Science and Technology in Poland. His research is focused on the generation of new agents of boron delivery for boron neutron capture therapy. But today we will talk about the second research interest of Dawid, which is the synthesis of new ultra-high temperature ceramic materials utilizing reactive sintering of mixtures containing different boron carbide form. So the floor is yours, Dawid.
I don't see that everything is all right. Everybody see the presentation?
Yes, we
Okay.
can. We can hear you.
Thank you for invitation. Just to be honest, it's glad for me to attend on this webinar after the Laura, because during my study, when I studied and the PhD, I read a lot of articles from Aura when I start some working on this new topic. Why I speak about reactive sintering? What is reactive sintering? We have a lot of definition. For me, the best is the second that I present, that reaction sintering is an alternative sintering process in which chemical reaction between the constituents of the green compound and its densification occur during the same thermal treatment. But types of reaction state, we have solid state reaction, involves reaction between solid powders to form a new solid ceramic phase, liquid phase sintering, and gas phase reaction. Some advantages. Everybody said that high purity could be advantages of the reactive sintering, control microstructure, and as Laura said a lot of about the microstructure, and enhance properties. But some challenges. Reaction control. Managing the reaction kinetics and controlling the temperature profile is crucial to avoid unresolved phases or incomplete reaction. That's the crucial thing during to choose this method or choose this reaction during the sintering. Homogeneity and complexity could be the same, the problem. But maybe some introduction why we are working. It's very similar to the presentation of the Laura. We are working on ultra-ceramic material because they have material properties between metal-like and the ceramic, and we choose two groups to sintering, borides and carbides. It was easier for us because during my PhD, I'm working on the boron carbide. And some advantages of this deboride that we use is ultra-high temperature ceramic material is that they have high thermal conductivity, high hardness, and formation of the layer of the boric acid that will help us during the sintering. Everybody can say, what is the problem? The problem is densification, and mild temperature through reactive sintering is attracting way due to chemical stable phase composition and microstructure as well as clean grain boundaries in the obtained material. So I started that during my PhD. I started working in the synthesized nanopowders of the boron carbide that it could be used as a rough material in sintering. And we have prepared, now they have the patent, European patent on this, how we prepare that very thin grain of the boron carbide. This is specific how we prepare the based on this, that we have a layer of the amorphous boron and on it a layer of the salt. And we can separate very pure powder. You can see that after sintering, we have the powder that is have only 1% less than graphite in this composition. And after that, we check this on the synchrotron Solaris line. Maybe some advertisement for the young ceramics that this is for you for free in the whole Europe. Everybody can apply it on the time on this line. And even you have the support to come to the Krakow and do your measurements. So on this research, we check that every boron carbide that was synthesized by us or it was commercial buying from another equipment have very thin layer of the boron oxide. Maybe this will be seen here. This layer is very important because it gives liquid phase during the sintering, and you can manage the reactive sintering using liquid phase. Of course, we have some results of this, and I can say my journey with the sintering of the ultra-high temperature materials in the SAS Institute in the Slovakia under the Professor Dusha group, the great time with the guys in this group, Ivan, Tamas, Victor, and other guys. And we start to assume the situation that what we do when we add something to have better sintering, only boron carbide. So we assume that if we have the non-reactive boron carbide that has more boron or the carbon in the structure, we have better sintering. So we add carbon, boron, we even add boron, and so that we have obtained more boron carbide, yttrium oxide, and aluminium oxide with yttrium oxide that we want to obtain garnet. And after that, we sintering. Of course, we have the different temperature of the sintering. Some additives have the lowest temperature, how some they have grown the temperature of the synthesize. But what is important that the carbon don't want to go to the structure of the boron carbide. It was very problematic, and the problematic was during the sintering that we have the graphite structure during the sintering, that the weakness of the structure of the composites. The same problem with the YAG, of course, and we obtain some results, and we can say the same in this image strong depends of the microstructure of sinteris bodies on the chemical and phase composition of the powders. Sintering was very problematic, maybe not so good as we assumed, but still we have some results to just thinking what we want to do in the next. So to sum up this time when I was during my PhD was that the density of the sinter material and their microstructure strongly depend on using addition. That is obvious. The obtained powder with additives are sinter with a high relative density, but the addition of carbon reluctantly builds into the boron carbide structure and weakens the mechanical strength of the composite. So the next part was some effect of addition of boron carbide sintering. Let us assume maybe we can change something. We can add titanium, boron, and titanium with the boron. We have better density, and we assume that titanium will go to titanium diboride. So we start the composition with the commercial boron carbide with addition 2 and 2.5, 0.10, 15, and 12% of the additives. And after that, we see how it's changed the temperature of the synthesize. The sintering process for the commercial boron carbide began at 1675 Celsius degree, as evidenced by the change in the sum dimension. All the percentage of titanium addition reduced the sintering temperature to 1600. The rapid densification of the composite sinter between 1600 and 2000 Celsius degree may stem from the axial mass transport between solid phase and the form authentic liquid phase, which can fill the pores. So this was a good option because we can fill the pores during this liquid phase. The result obtained by our research group can be compared to the boron carbide with titanium but silicon carbide, and the same with the hardness and other things. So it's quite good because we don't assume this. Maybe some interesting information is during additives of the boron, we have the situation that the boron take the residual graphite that is obtained during the sintering. So we take the boron can take the carbon to the structure, and we don't have the free carbon in the composite that weakens the structure of the composite. We can see the table formation and some analysis. It looks quite good, but we say, okay, we have some results, very interesting. By increasing the sinter temperature, the boron carbide stoichiometry converts from boron carbide B4C to B14C2. The boron additives weakness the mechanical properties as enter the structure of the boron carbide, and the applied titanium and titanium boron additives and the sintering technique also improve the mechanical properties of the obtained composite due to titanium diborate phase formation. So the next we have article, and now it's the main focus that Laura said that during some results that we obtain, we assume that we need to change our point of view. So moving to the scope of the work, the aim of this research was to obtain composite based on boron carbide and intermetallic compounds from TIESI system. To achieve this goal, we used 3 different methods of the sintering: free sintering, hot pressing, and SPS spark plasma sintering. Thanks to so much planned and performed tests, it was possible to access how the technology of the method affects of the properties of the material. the difference between the technique as well as how the amount and type of additive affect the final properties of the material. For the starting, we use two composite system using this. This system was titanium disilicide and titanium 5 as silicon 3. So we assume two reactions. It was considered, it was assumed that dominant phase in the resulting product should be silicon carbide, titanium diboride, and titanium carbide. So after that, we prepare the samples, compare the results with additives of this intermetallic 5, 10, 15, and 20%. And what is most important in our research during this, what we assume, we start with stoichiometric measurements, stoichiometric sample. The stoichiometric sample, that's meaning that we assume that 100% of our raw material during the sintering will be changed in another phases. So in this method, we think that it should be look like this. This reaction should not ever exist during the information that we obtain from a lot of articles, but it exists after our results that showed. For energy reason, reaction is more favorable, leading to the formation of the products such as titanium carbide, titanium diboride, and silicon carbide. But thus the expect products of reaction sintering in the mixture of starting powders are composite consisting of this chemical compounds. In the case of reaction taking place into the system, it was formatting only titanium diboride with silicon carbide. So maybe another question, how to calculate the data, how to prepare the data. I find very good program that is free for you use. The software is called OpenCalculate. Everybody can use this. And this program is free thermodynamic software that can, for calculation and multi-component equilibrium property and phase diagram and for database development, and it could help you with the calculation and help you to assume what we can obtain after the reaction. So now we can see the results of the phase analysis of the obtained composite. This on the ending are the stoichiometric composites that we see that we don't have the boron carbide in the structure. We have only titanium diboride, silicon carbide when we use titanium disilicide, or we can titanium diboride, silicon carbide as residual amount of the titanium carbide, and it's only obtained that the situation that we don't have the free boron during the sintering. So with the increasing percent of the additive in the form to this intermetallic, the boron carbide is disappearing and we obtain only titanium diboride, silicon carbide, or titanium carbide. Of course, if this free method, we can see this, but the main problem, because everybody said that SPS is a very fast method to get the quickly results, but in this method, we have more problem. It's similar that we can change the temperature of the synthesize and starting close to 1100 Celsius degree to 1200 Celsius degree. After that, it's not stable as two earlier method like free sintering and HAPA method. And for that reason, the temperature is of course lowest than typical. In the free sintering was 1650 Celsius degree. To compare to SPA method is less about 400 Celsius degree, but still we have the point that it's not very good homogeneous. So sometimes you have the parts that the method is very fast, so it's problem with the homogeneous of the whole composite. It's only the difference about 1 or 2%, but still you can something have, you can obtain something in your samples. Here we have some properties of obtained material from different additives of intermetallic. We can see that in the presence of the results of physical and mechanical properties for the obtained composite, comparing to the results for given methods, The above graph showed that for additive in the form of titanium disilicate, we have high results of both density as well as hardness, Young module are observed. So it's quite good. We have better densification. We have better composite after the sintering. The same situation for another additives of intermetallic, but it could be more problematic to compare these two intermetallic. It's better to add titanium disilicate, and with the lowest the temperature of the synthesize. And now to compare, after the synthesize, we obtain completely sintering. Sorry, after the sintering, we obtain completely different composites. That when we use titanium disilicate, we have only titanium diboride with the silicon carbide and residual of the intermetallic. And when we use titanium 5 Fe3, we obtain composite with titanium diboride, titanium carbon, silicon carbide, and the less than 1% of the intermetallic. So you can see how we can change, how we can assume before the sintering the phase composition of our obtained composite, how we change the temperature of the synthesize, that typical boron carbide start close to 1700 Celsius degrees sintering. Now we can lowest the temperature with different method and different additives of intermetallic. And even if you want to obtain completely new composite, we can, in the SPS method, change the temperature to 1250 Celsius degree. So it's quite good for us to obtain something like that, because now we want to save the energy and save the cost of the production, and still we can grow some temperature to have better homogeneous. This is the result from the synchrotron line in the excess spectra line. And this line was very interesting to compare the result from the XRD measurements. Because in the XRD measurements, even in the lowest temperature, about close 1150 Celsius degree, we show that we have the phases like titanium boron silicon carbide, but still they are not well homogeneous. So we can compare these results with this spectral line in the synchrotron Solaris with my colleague Rasha, and we compared that this method can support analyze only support analyze ultra high temperature ceramic materials, how they are well synthesized. And after that, we check the microstructure. Of course, we can see that we have worse microstructure in the method like free sintering. We have more porous. And it's obviously because some carbon from the boron carbide is removing like carbon dioxide. In the HP method, we have better microstructure, and the same situation with this with the SPS method. But in the SPS method, you can see something like that. That was very fast sintering. So sometimes we have residual after the intermetallic and different composition in this part. Not very homogeneous like in the HP method, but we have a lot of liquid phase during the sintering, and we have a lot of pores like in typical free sintering to compare this SEM that we obtain. And of course, we have some publication of this. So maybe to conclusion, this part of my work was that due to presence of the liquid phase from the intermetallic material, it is possible to lower the synthesis temperature from 2000 to 650 Celsius degree in the typical free sintering. The titanium carbide phase is formed only when no boron, free boron, is present in the system during sintering. The microstructure and mechanic properties of our obtained composite ceramic can be effectively tuned by regulating the combination of the composites of the starting precursor used in particular through the use of various intermetals from the TASE system. Both additives tend to be characterized by similar hardness value to each other. A higher hardness is obtained for the addition of intermetallic titanium disilicate. It's obvious because we have more silicon carbide. In relation to the addition of titanium 5 Fe3 are associated with obtain, as I say, more silicon carbide, which has a higher hardness than titanium diboride. So before starting sintering, you can think about the composite and what you want to where you want to use these composites, in which application. So you can control the phase after the sintering, and you can control after sintering the proportion of ceramic phase in the composite. It's very good for you to think why I want to obtain this composite in which application, because now we do a lot of experiment and we want to say that I obtain something. But in my opinion, the best option is why you want to obtain something or what you want to do with this material. And now I can show you to comparison that what I do during my JECTRAS mobility, and I was very thankful that I obtained this JECTRAS mobility, that I spent 2 months in different institutions. One was in the Zeitek when we sintering some composites, and the second in the Czech Republic, and the second month I spent in the Slovakia in the group under Peter Tatarko says in Bratislava. In the Czech was under group in Dawid Salomon. So it was a great time for me that I prepared the material and see where I want them use. So we check the thermal diffusivity of this material, and you have the comparison of the temperature dependence of the thermal diffusivity of sinter composite using variable intermetallic and to compare to boron carbide. I don't know that you see the movie. Maybe now it's not working, but after that I can show that we checked the ablation research test and was using the oxyacetylene flame at 1800 Celsius degree, and material was exposed flame during 60 seconds. So we can see that we prepare the composite and we want to see how they are look after this method. Sorry, and to compare, you can see how it looks typical boron carbide after something like that, that they crack at the temperature about 1600 Celsius degree to 1700 Celsius degree, how they are cracking. After, when you use with intermetallic additives titanium Fe3, we can see that it was little bit changed the structure, and we have the problem. It was not so good. The same with titanium disinfect. But of course, we analyze everything, the surface, how it's influenced. But now we can present you the result of one material. It was preparing during my JECTRAS mobility, that this material, nothing happened on the surface during this ablation test. And now we can assume that it's success or not. Of course, that is always the question. We need to work more on this 2 or 3 different composites that are showing you that was using the reactive sintering during the sintering. And you can imagine that this material was synthesized in the lowest temperature lowest than 1400 Celsius degree, but it was working in 1800 Celsius degree. So what was quite good for us to obtain this material. Now we check for wait for some patents. So after that, I can publish results. But to summarize, the optime composite and the thermal resistance are influenced by intermetallic additives, which allow lowering the synthesis temperature and the thermal diffusion. The obtained composite show higher thermal resistance than commercially available material or composite obtained from pure boron carbide. When intermetallics are used, even from the same system for both TE-SE and TE-AL, similar difference can be observed after ablation test. But it's also possible to obtain components from each system that are resistant at 1800 Celsius degree. So we can obtain from each system, calculate the phase after the sintering. Now we exactly know how to calculate this, how to obtain good materials to the application, to the aerospace application, to the application of the gas turbines. And now I want to thank you, because during all my journey of the PhD, and now after I stay at the university, I have great opportunity to have a lot of internship and have meet a lot of great people that they helping me during all this research. Of course, they give me a lot of knowledge. And now, to summarize, now even now, I'm present you on the webinar, I'm staying in the cerams in the France, that we are working on the 3D printing by the robocasting of this material and using this material in application that we can 3D printing some element it will be using in the maybe in the future in the aerospace. So maybe what I can ask during my knowledge, during my research, that the first thing is to, when you try to do something and try to prepare some materials, just think where you want to use them. And even during your career and during your research, you think it cannot possible to use in this application, you can find another application. And never give up, because I have a lot of time during my PhD that I was quite, I don't want to continue my research work. So only to do is let's do it what you want and have fun from your research. Thank you.
Thank you, David, for amazing presentation. And I would like to say I really appreciate how you highlighted the role of the community in your work, because, you know, together we are always stronger, right? So that's pretty cool. And now I would like to invite everybody in the chat to ask questions to our speakers. And we already have 2 of them. So I believe the first one is for Laura. And the question is that I have difficulty in preparing ceramic samples for TEM as they break very easily while polishing. Could you give some guide in that?
Everyone has difficulties. You're not the only one. Just be patient. Don't rush the final step. If you do it mechanically, yeah, don't rush the final step, because I remember at least 2 or 3 times that I was achieving almost the 20 microns, and then 2 slide more and the sample was gone. So don't need too much. Go slowly and yeah, be patient.
Maybe I can help.
Be patient and hope for the best.
Yeah, but sometimes, sorry for that, Laura, but sometimes when we bought some equipment from the Struers, a lot of companies have the information how they're polishing your sample. So sometimes it's very good support to check the company that's selling you the equipment, that maybe have some information how it's good to polishing this. Of course, it's not that helping you in your sample, but yeah, we know this.
Borides and carbides are really bad beasts, and
Yeah.
if you give them to professionals, to the people who sell fib, they will give you samples that are really not usable because they are used to prepare silicone. Okay, thank you.
Yeah. Okay, we have second question related to TEM, which is, does the sample preparation for TEM involves fib in situ lift or lift out or other?
So I prefer the mechanical thinning, because with the fib you have a very limited space that you can check. So unless a specific case where you have, for example, under an indentation or a specific oxidized spot, I prefer mechanical thinning. And even with the oxidized samples, the group in Darmstadt is really wonderful in preparing samples, because all the lamella, the samples that you've seen on the oxidized samples were done there by great students, by their techniques. Yeah.
Thank you. Another question is a bit longer, but I will read it. So Marv says that I'm very impressed with the idea about boron carbide. Just as you said earlier, particularly in conclusion, the applied titanium, and titanium boron additives and the sintering technique also improve the mechanical properties of the obtained composites due to the titanium diboride phase formation. Are there any limitations or challenges associated with using titanium and titanium boron additives in boron carbide composites?
A very long question to ask, because it always could be the problem, because when we add titanium, you need to think about one thing. We take the boron from the boron carbide structure. So that's the first information. So it is very hard to sintering like this. We can have some problems during the sintering. Of course, exactly the temperature, everything, it could be start the problem. Sometimes, as I show in the presentation, we add a little bit boron during this event with titanium to avoid the situation that we have more pores, because it was reactive sintering with titanium with the boron, and it could be take boron from the boron carbide structure. Boron carbide is very specific material, maybe I said from this, that is non-stoichiometric. So first, what you need to do, and to be honest, you need to check what you obtain. Because I remember one thing, that we obtained the boron carbide from the one company, and they said that the structure is close to B4C. It never exists, it's close B4.2, but still. But it was completely different, because in the boron carbide we have close to 6% of the amorphous boron. So to check what you have, even when we bought the boron carbide commercial, sometimes there's additives of the free carbon, about 1%. And this free carbon is added to the sintering. So still you can have something like that. So first, what I need to say, you need to check what you have. If you want to have commercial, check the commercial powder. After that, giving the titanium, it will help you with the sintering, but you need to avoid the situation if you have too much titanium, you have too many liquid phase. And this liquid phase can break your composite. I think Laura can say something about this.
I agree.
Maybe some digression. I remember when I started my sintering of the boron carbide with one article, it was funny situation. It was 3 months of my start PhD. That was one article that is possible to sinter boron carbide less than 1000 Celsius, under 1000 Celsius degree. And you can imagine, I tried to prepare this. Once time I tried, my boss checked the result and said, no, nothing working. After the second time, he said, it's something problem with you, of course. I don't believe that you do something stupid. And you can imagine, third time, it was a situation that my supervisor came to laboratory. It was quite very funny to see him. He do everything as in the article. And after that, he checked and said, I still don't obtain boron carbide. And you know what's the problem? In this article, they take the XRD pattern, but not from boron carbide. And they said that is boron carbide.
Oh.
So to be honest, we have now a lot of articles, a lot of information. I prefer something like that to when I have some proposition to start 1 or 2 samples, I check what I obtain after the sintering and check the rough materials. Even the titanium you obtain, the crucial could be how the size of the titanium you have. Even this could help you with sintering or still have more problem. Because if you have bigger titanium, you have more liquid phase in one area. Sorry, I'm too long.
That's all right. So thank you for the answer. So next question is for Dawid. Elia asks, I missed where you did the OAT tests.
OAT?
OAT.
Ablation test, I think. Oxygen ablation test. Yeah, it was under the Professor Tatarko group in the SAS Bratislava. They are open to cooperative, and Peter Tatarko is person that is always smiling, always joking with me, David, it's good sample, this is not good, what do you do? So it was amazing time for me and with him. And even if you write to him, he always responds to the email, and you can send him the sample and he can prepare for you the results and resend. So this is the guy that is good to cooperate it. And maybe
I fully confirm that.
and maybe to be honest, to get best results, you need to find good people, but always smiling and won't always cooperative and hard. Because sometimes you cannot obtain good results for you, but still, if they want to help you, you have more possibility to obtain success.
Yes,
And
I 100% agree with that. All right, so we have a couple more questions. The next one is from Rajat, who is asking, I'm using the gel casting process for fabrication of fused silica-based ceramics. I want to reduce the sintering temperature from 1300 degrees to 1100 degrees. Can you tell me some additives that I must use to reduce the sintering temperature? Maybe it's slightly, yeah. Do you have an opinion?
I think it depends if you can have something at the boundaries. If you want pure silica, it's not just, I just need to reduce, just put some other oxides.
Yeah.
Now I'm doing this in the terrains because I started robocasting of this material. To be honest, 3D printing is a very hard method, specific for the ultra high temperature ceramic material. Because as Laura showed in the presentation, and we can package 60% of the powder, now we obtain some result that even more, but it's very problematic that you have a lot of organic phases. And these phases and during the sintering could be give the problem. I cannot give you, use this, and will be everything all right.
Yeah.
At first, I would say
maybe I have the proposition
other
because it's very interesting question. I can give my email, or you can check my email, right? And I try to speak with you, and maybe we can figure something like that. Because now I don't have an knowledge that you add this and will be good. So I need to think about this, to be honest. But still, please write the email. It's not a problem.
Right. Laura, you wanted to say something?
You know.
No. Okay. So we can move ahead. Next question is from Mutu, who is asking, did you observe any new phases like boron oxide after the ablation test?
Yeah, it depends on the sample, because as you see in the first two samples that I'm showing, we have new phases and it was oxide on the surface. Now is the measurements, of course. But in the first sample that I'm showing, that we have the material that look the same before the sintering, we don't see another phases. So it depends on the composition. It depends what we have, which phases we have before ablation test. So yes, of course, it depends on the material, and we see these phases and this boron oxide. Even, of course, I don't want to see every composite. Even we have the situation that we have very thin layer that was very protective the samples, and it was the boron oxide. So yeah, we observe this.
Thank you. So if you have any other questions, please write them in the chat. I have one question. It's the same one for Laura and Dawid. So first I will ask Laura. Just imagine you have the knowledge you have today. And if you could go back in time to the time when you started this research on this topic, what would be one piece of information that you would tell yourself? Take your time.
Wow. If I could broaden a little, yeah, have a more basis, I would get more basis on finite element modeling, which is something that it's needed, and I'm really, walking in the fog.
Okay, so just get out of the lab and start modeling.
Yeah, sometimes when it doesn't work in the lab, go something at the computer.
I think that's good advice. That's really nice advice. And for you, Dawid?
Third question for me, because everybody who knows me, everybody knows that I don't want to say what I do earlier if I have the knowledge like this, because during all my life, I do things that I think that in that time, that my knowledge, I do the best, you know? So,
yeah, of course.
Yeah, of course. So I cannot say something like that, but maybe one thing, really, and maybe this is important, just look for opportunity. It's a lot of projects like JECTRAS, Erasmus that I obtained. Now I obtained from the France embassy in the France to move from your department, because after you start PhD 1 year, you can get the knowledge from the department, but take the possibility to go to another department and see how the another people are working and how they working, and you can compare with your result, because it's for you it's to open your minded, because I always try to avoid the situation to stay in one group and everybody said everything is good. Just contact with people and have the opportunity, because now during the European Union and this project in the European, or even you have project for the go to United States and other country like Fulbright, you have the possibility to see how the different group working and different point of view. For me was that was last time was in the April of the conference about the ultra high temperature ceramic materials, and see how the Korean working, how the people from the Italy working, from the United States, how is the different looking on the same materials.
Yeah.
Even I see, maybe what I see, that I don't always want to get the material, as Laura said, but sometimes it's better to think how to calculate this, how to have some models to avoid the situation we lose materials. So maybe it's to open your minded and go and stay even 1 month in different department could help you.
Yeah,
Maybe this.
I totally agree. I myself learned the most abroad, so that's great piece of advice to everybody. We have one more question. Any advice for young African researchers who are struggling in their research projects in terms of equipment deficiency?
There are programs, but I don't know if there are restrictions. The NFFA program where you can apply for a specific equipment and you can enter this circuit. But honestly, I don't know if there are some requirements of the applying country. But I can check the website and send it on the chat.
That would be amazing. Thank you, Laura.
I have another, because we have the great opportunity that with my chief of department, we are working cooperated with the UNESCO program, and UNESCO program take person from the abroad from the European Union. AGH have agreed on this, and different university in the Europe that the people can come to Poland or the AGH and work in our, of course, department for own researcher, and it's half a year, so it's quite good option to use the UNESCO program. And I know that UNESCO support people from every country, because we have the students from the Ghana, or other part of the Africa, so I think it will be easier option to even find this UNESCO program. I can even now check the UNESCO on the website and say the information about this. So
that would be amazing. Thank you, Dawid and Laura. I will ask once again, do we have any last question?
There was a question, private, if I use some, which method, I don't know if it was, yeah, for material preparation, but I don't know if it's with the one with the fibers or the bulk materials. So for the bulk materials, I just use powder metallurgy. And with when I use short fiber, I use again powder metallurgy. So ball milling, wet ball milling, and hot pressing.
I'm sorry, I probably haven't seen this question because
it was private, but
oh, okay. Any private questions to Dawid?
No, I don't have.
Okay.
Or maybe I don't see. So I have the last information.
Thank you.
That I sent only from the UNESCO program, from the EGH, even if somebody wants. So I think this UNESCO, it will be help some person.
That's amazing. Thank you so much. So I think with this, we can conclude the webinar. So thanks to, first of all, the speakers for their amazing talks. And thanks to all of you who joined us today. I hope you all had a great time and you will join us next time too. Bye-bye.
thank you. Bye.
Thank you very much.